Okay, so this is the lecture for Monday, November 6th. What we're going to be talking about is we're continuing our discussion of bootstrapping. So let me jump to the notes here. Okay, so recall that the idea of bootstrap is to try and assess the uncertainty of a parameter estimate. And our plan for discussing bootstrap was broken into two parts. The first part was to obtain the bootstrap sample, and we spoke about that. There are two ways to do that. You can either do a non-parametric bootstrap sample where you resample from the data you observe with replacement. That gives you a new bootstrap sample. You can calculate your parameter of interest, which we've been talking about, the mean, and you can do that over and over and over again. Alternatively, you can do a parametric bootstrap where you fit a distribution, and then so fitting the distribution involves estimating the parameters that describe that distribution, and then you sample from that fitted distribution, which is of course distinct from the true underlying distribution whose parameters we don't know. Either way, you obtain a bootstrap sample, and then what you want to do with that bootstrap sample is do something useful with it. So you want to describe the uncertainty of your parameter estimate. And so we spent some time in the last class talking about mean squared error, bias, and variance, and we started talking about the producing a confidence interval. So let me jump to, so this was our mean squared error discussion from last time. Our estimate of the mean squared error, the true mean squared error, would take estimates and subtract off the truth, square them, add them up, divide by the number, so you get the mean squared error. But of course, we don't know the truth, and we can't sample from the true underlying distribution. So our estimate replaces that with replaces the truth with our estimate from our original sample. And then this is the parameter estimate from each of our bootstrap samples, and then calculate the same thing. We also talked about bias and variance of the estimators. Okay, so we then started talking about confidence intervals. And the first confidence interval we talked about was the percentile. And so let me jump to R here. Okay, so what I have here on is a plot of our bootstrap sampled mean. So what we've done is a non-parametric bootstrap. I've run the first lines of the bootstrap.r to get a histogram of bootstrap means. This vertical line here at 1.78 is our estimate of the mean obtained from the original sample. And then what I've shown here is the 0.025 quantile of our collection of bootstrap sample means. This is the 0.975 quantile, and so if this is 0.025 and this is 0.975, the middle should have an area of 0.95, and this seems like a very reasonable method for obtaining a 95% confidence interval. Nicely, it would seem, our confidence interval is going to be asymmetric, so the distribution of the bootstrap means has this right skewness. If I use this simple method called the percentile method, the distance from my mean to the lower bound of my confidence interval is going to be this distance here, which is smaller than the distance from my mean to my upper bound. And intuitively, this feels right because our confidence interval is right skewed. Our distribution of sample means is right skewed, and it seems like that should nicely describe the uncertainty. It turns out, however, that we actually don't want our, well, it can be argued that we don't want our confidence interval to have that same right skewness as shown in our sample distribution. And to illustrate that, at the end of class last time, we did this last section of the script with Bootstrap R, beginning at about line 100. What we did was we returned to the true underlying distribution. So recall that bootstrapping is trying to mimic that idea of resampling from the true distribution, which in practice we can't do. But in simulation world, we can. And so this histogram is the true distribution of sample means. If we were to resample from our underlying distribution over and over again, we have the true mean of 2. Here is the 0.25 quantile of that true underlying distribution, 0.025 quantile. Here's the 0.975 quantile. And so what we could do is the same game of using this distance from mean to lower quantile to get our lower bound of our confidence interval, mean to upper to 0.975 as the distance to our upper bound, and use that to construct our confidence intervals for the sample means. And so doing that repeatedly gave us this picture where these are our confidence intervals. At 2 is the true sample mean. And what we see is that when we miss, we tend to miss only to the right and rather than to the left. And by doing some math, so let me go back to the notes here. Doing some math with the true underlying distribution, what we did was we just applied algebra inside the parentheses here, and we ended up with a confidence interval where it was basically flipped. What we had was this, the 0.975 quantile appears in the lower bound, the 0.025 quantile appears in the upper bound. And so we end up with a confidence interval that is left skewed. But what we see when we apply to the when we ran that, we get confidence intervals that appear more balanced. So one could argue that if our sampling distribution is right skewed, as we saw, we want our confidence intervals to be left skewed. Now having said that, can be, it's probably a little confusing to us, and we're the professional statisticians in the room. You can imagine how confusing that is to to trying to explain that to your boss. But so let me return to the notes. I think we're back up to speed. And okay, so again, this percentile method just says take the 0.25 quantile, 0.975 quantile from your bootstrapped distribution, construct your confidence interval from those. And unfortunately, this is not very accurate. We saw that the coverage rate was a little bit bad, but more importantly, we saw that it seems to be imbalanced in the direction that it misses. So we talked about this, which was done for the true sampling distribution, which isn't known. So how do we mimic that with our bootstrap sample? Well, the idea is to use a pivot. And if you go back and you look at this math, what we ended up doing in some sense was pivoting around the true parameter mu. So the statistical definition of pivot is a function of observations and parameters whose probability distribution does not depend on the unknown parameters. But I think that doing the math illustrates that notion of pivot a little bit better than the definition does. You've seen pivotal statistics before. If our underlying distribution is normal, we know that standardized by the mean and by the true standard deviation would give us a standard normal. When we have to estimate the standard deviation or estimate the variance, so we have an S squared here rather than a sigma squared here, then that distribution is a T. But you can generate that T confidence interval by doing math like we just did, where you pivot around the mean. Okay, so let's see. Okay, so we're going to look at two other methods for bootstrapping, and the first is the basic bootstrap. And so what this top bullet here assumes we're working with the true distribution. So here is the true parameter, here is our parameter estimate. And so I'm going to look at this here. You start with a probability statement that's true, which says this has a probability of 1 minus alpha. Let's just use alpha as 0.05. So this is 0.95. What we're finding is a 0.95 confidence interval. And if we knew the true distribution of this theta hat minus theta, then the probability that it would be between the 0.025 quantile and the 0.975 quantile would be 95%. And so if you then solve for this, so just like we did on that previous slide, what we do is we subtract theta hat from all three sides of this inequality. We multiply through by a negative to get to have a positive sign on theta, and you do that math, you end up with this confidence interval. And what we see is that the 0.975 quantile appears in the lower bound. We started with it over here, but after doing the math, that 0.975 quantile ends up in the lower bound. The 0.025 quantile ends up in the upper bound. And so this confidence interval is reversed in its direction, just like we saw before. Now, that would be what you can do if you knew the true distribution. So in bootstrap land, what we do is we replace the true unknown parameter with our estimate obtained from the original sample. We replace the estimate with our bootstrap samples. And so that's exactly what's being said here. Here is our estimate from the bootstrap sample. Here is our estimate from the original sample. We can get the quantiles of the distribution of theta hat stars minus theta hat. And then we can generate our pivotal statistics just like we do here. And again, that 0.975 quantile appears in our lower bound, and the 0.025 quantile appears in our upper bound. Okay, so I'm going to pause the recording here just because it's easier to upload smaller videos. We will pick things up. We'll do this in the R code next.